So the second page has general vocab main ideas, and then on the back of it has some of the some stuff on units that are going to be important for the midterm. So for these vocab words, there's not really much to go over in too much detail. It's mostly just some of the terms you have to memorize. But a couple ones I'm going to point out are the difference between these two right here, fundamental units and derived units. So fundamental units, that one was Q, and derived units, that one was I. So let's look at those definitions and make sure we understand the difference between those. So fundamental units are these seven right here: kilograms, meters, seconds, moles, volts, candela, and Kelvin. These ones are the units that we use in physics to represent mass, distance, time, amount. Moles is like the chemistry unit. Volts, and then candela is like an intensity, and then Kelvin is temperature. And so any other unit that's not one of these seven is some conversion from those seven, such as like grams, would be therefore would be a derived unit, which is I. So things like meters per second squared, miles per hour, or newtons. All of these are made up of other units. So for example, newtons is made up of a mass, kilograms, times meters per second squared. So you can see that within newtons, there's actually three fundamental units: kilograms, meters, and seconds. And so that's what makes that a derived unit as opposed to a fundamental unit. A few other terms to go over: accuracy versus precision, number 7 and 8. And so precision is letter D, and accuracy is letter A. So let's look at those ones. So precision says the closeness of measurements to one another, and accuracy says the closeness of measurements to a real or accepted value. So the reason why precision is closeness of measurements to one another is an experiment can be thought of as being precise if you do it many times, and all of the times you measure it, it's about the same thing. You get the same number as a result. So let's say we're measuring the length of a stretched spring, right? And we measure it with five. We measure it 5 times with the same weight, and we get the same distance stretched within, a couple millimeters. That would be very close together, so that would be considered very precise. But if we actually look at whether that was an accurate measurement or not, that's determined by whether or not that number that we measured is close to the accepted value or the real value, the one that we want, the theoretical value for this. So if we're measuring gravity and in an experiment, and every time we do the experiment, we measure it to be 10.1 meters per second squared. So we could say that that measurement is precise because we're getting 10.1 each time, but it's not accurate because it's not close to the 9.8 from gravity. Okay, so that's another one there. Vector versus scalar. This one you should hopefully know by now, but vector is W and scalar is R. So vector is the physical quantity that has both magnitude and direction versus the physical quantity that only has magnitude, which is scalar. So if it has a direction to it, it's a vector. Right? Let's look at this. So the distance, displacement, speed, velocity, acceleration are all our kinematics terms. And then projectile, trajectory, and range are our projectile motion terms. The range here is s. It's the horizontal distance covered by a projectile. And then one more distinction I want to look at is mass versus inertia. So mass is F, and inertia is C. And so if I look at those ones, the reason why mass is F is it's the amount of matter that makes up an object versus inertia, which is the resistance to change in the state of motion. So an object's mass controls how much inertia it has, but the property that we, when we talk about resisting motion, we say that that's inertia. The rest of these are online, so you can kind of look through the rest of the solutions here. We'll move on. On the second page of this sheet, we have to sort these categories into scalar versus vector. And so you can put, for the scalar categories, this is going to be your distance. There's no direction with distance, and speed. There's no direction with speed. Versus the other four are all vectors because they all have a vector quantity. They all have a directional component to it. Displacement has direction. Oh, look at that rainbow color. It's nice. So all four of those go into the vectors. Okay, so make sure you know those. The difference between, again, that goes back to that definition. One, scalars have only magnitude, only a number component to them. Vectors have both a magnitude and direction. All right, and then here is another talk about fundamental versus derived units. So list proper units for the following quantities, include whether this is a fundamental unit or a derived unit. So when we say proper, we're talking about what we generally use in physics. So for distance, the proper unit we use is meters, not kilometers or not miles or centimeters. So meters, and this is considered to be a fundamental unit. Our derived units are made up from more than two. So for speed and velocity, the proper unit for that is meters per second, both for speed and velocity. This would be a derived unit because it's made up of two other units, meters and seconds. Acceleration would be meters per second squared, also a derived unit. And force would be newtons. Now this looks like it's only one unit in itself, but remember that a newton is a mass times acceleration. So it's a kilogram meter per second squared. And so this is also derived. All right, and that's it for the second sheet there.